Hi, everyone. Thanks for inviting us today. We're going to talk about automated model exploration. Before we jump in, let me quickly introduce ourselves. I'm Sandeep, and I'm a technical program manager in the artificial intelligence team at LinkedIn. And I have with me my colleague Jun. Jun, do you want to introduce yourself?
Sure. This is Junjia from LinkedIn AI, and I'm glad to be virtually here to talk about our work. And Sandeep will start with some overview about this project. And Sandeep, please take it away.
Thanks, Jun. Now let's go over some of the agenda items that we'll cover in this talk today. First, we'll talk about the motivation behind automated model exploration. Next, we'll provide a brief overview of LinkedIn's machine learning platform. And finally, we'll dive deep into various components of automated model exploration. Let's get started. The typical development cycle of machine learning engineers is like this. First, we start with a bunch of data. Next, we analyze the data, select features that we think are useful. Then we prepare the data and feed that into our trainer for training. Finally, we do model evaluation on the test data set. If the results aren't promising enough, then we go back to step one. As you can see, there are a lot of repetitive steps in this process. Ideally, the entire process should be much simpler. We ask users for minimal information such as label data and minimum metadata such as label field to entity mapping. Then we launch the offline pipeline for the users and voila, you have a model ready to use. Wouldn't that be great? This is exactly the goal of automated model exploration, to automate standard model training practices such as feature selection, hyperparameter tuning, model selection, to democratize AI and speed the path to make an impact. Before we dive deep into various components of automated model exploration, let me share a brief overview of LinkedIn's machine learning platform. Productive machine learning, or in short, ProML, is LinkedIn's machine learning platform with the goal to improve productivity of engineers. This slide is a little old as we have been constantly making changes to our stack, but overall architecture remains the same. This is an overview of the key components of ProML, and I'll go briefly over a few of these. First, feature marketplace. Each machine learning models need features, and feature marketplace is one-stop shop to share and discover features. After features are selected, ProML notebooks helps with writing feature transformations and visualizing them interactively. After we have features, feature transformation computation, and model structure, we can use model training tools to train and evaluate models. Here, the auto train component that you see is basically the automated model exploration module that we're talking about today. Model registry stores training output and metadata. It also helps with search and discovery of previously trained models. Once we have model ready, this model deployer module helps with deploying the model and tracking the progress of deployment. Models are deployed in production through Inference Engine. And after deployment, the health monitoring component measures the performance consistency between online and offline world. It also sends alert if any issues are detected. Now let's talk about various components of automated model exploration. We'll go into more details later. First, data sampler. Normally the size of training data is huge, billions of records with terabytes of data. Hence, we need intelligent sampling algorithms to reduce data while preserving data characteristics. This way, we can run multiple iterations at reduced compute cost. Second, we need a feature exploration component to explore many feature sets in parallel and identify useful features based on, say, L1 regularization or other statistical techniques. Third, automated hyperparameter tuning. As the name suggests, to automatically tune hyperparameters, instead of exploring them manually. Fourth, Algorithm Explorer to explore various algorithms such as linear model, tree-based model, or deep neural network models. And finally, a model selector component to select candidate models based on offline objective of the problem, such as AUC, NDCG, etc. Now I'll hand over to Jun, who will go deeper into each of these components. Jun, take it away.
Thanks, Sandeep, for the overview. And our automated model exploration is mostly focusing on the model creation side. And for our problem setup, it's mainly about supervised learning. And it can also be regarded as a multi-dimensional search or optimization problems. And we're trying to optimize the desired model metrics. So as the example shown here, if we take a very simple grid search approach, and suppose we only have two sampling or grids in each of dimension, we will see that we can demonstrate the problem like this. Let's say the first dimension is about the sampling. The second dimension is about the features, and in the third dimension is about the algorithms with their hyperparameters. If we have, like I said, if we have two grids in each of the dimensions, we will end up with 8 points in the search space to explore. So once we choose this one of those points to explore, we will need to turn them into actionable workflows. And how with this will demonstrate how we're actually turning this one search coordinate into the optimization target, the actual metrics. So first we do the data sampling. After the data sampling, we will join the data, the observation data, with our features. And those features are entity-based features that are available from one component mentioned by Sandeep. It's about the feature marketplace. So we have a central place to host those entity-based features. After we join those features with the observation data that we have, then we will start our feature selection process. After the feature has been selected, we will turn them into training data and feed them into the actual model training process. Then in the end, after model is done, we evaluate the model on holdout data sets, which will give us the metrics that we want, or the optimization target functions. Now let's dive deeper to each of the components. First, let's talk about the data sampler. So the goal for data sampler is to reduce the size of the data so that we can speed up the exploration process. But also, we want to get indicative signals from the sample down data to the full data set. So there is an aspect of the transfer learning over here. We notice while we're doing this, we notice that there's no universal sampling strategies works with all the algorithm that we're working with. So we have specialized sampling strategies for different problems. For example, we will use stratified sampling for regular solutions, where we will do a random sample based on each of the label types, for example. And for personalized model or more specific, this is some popular model within LinkedIn. We call it GeoMix. And we will need to use entity-based sampling to make sure that we can get indicational signals. And for learning to rank, typically we'll use group-based sampling, which is another type of stratified sampling. The next component I want to talk about is about the feature selection. And there are quite a few different strategies for feature selections. And we finally settled down on the brute force raw feature selection. How basically that means we gradually adding features or remove features into the current database, current data set, and carry out the whole training process to get the metrics. Then we decide if this feature is useful or not. The reason for choosing this method is because, for one, it's very reliable. For two, it's method independent because we're dealing with different training algorithm later, and we want to have a universal feature selection mechanism that works for everything. And one thing worth mentioning is that is about this interaction of feature. As I mentioned before, our feature are typically entity-based, and to have interactive features which plays a big role in the final model, we need to consider about this. And for deep model, typically it's handled it's automatically handled by the layers of the neural nets. However, for other shallow features, shallow models, we need to take interactive feature creation into account and manually create. So the last step is about choosing a specific algorithms to carry out the training process and to produce the metrics. So we have mainly three categories of different algorithms. Geomix, that's a linking personalization model. XGBoost is a very popular tree models. Then there's a big category of deep learning models. And we have a universal language here, which is called Quasar. It's a LinkedIn DSL to abstract away the representation for this different kind of models so that we can easily handle a different kind of model in the same environment. After each model training process, the trained model will be evaluated on a holdout data set based on a desired metrics. Those metrics are pretty standard ones. I list a few here. It could be the EUC or it could be NDCG. And this very last component, model selector, would collect all the models from the points that we have explored in the search phase and generate a report. With this report, we will select the best performing model and end our initial journey on the automated model exploration. We're still at the very beginning stage, and our focus has been on automation and how to play nicely with LinkedIn's machine learning platform. I'm looking forward to the future advancement down the road. This is a team effort, and I would like to extend my appreciation to people here. And please do not be mad at me if I leave it out, and there might be more people than I can remember. And of course, more importantly, we would like to thank you for being here, listening to our talk. Thanks.